Good morning. Can you see the screen?
Yes, sir, it is visible.
Okay. Are the TS there?
Yes, sir, available.
Okay, so you can start recording. So let us continue from where we left off in the previous class. So we were discussing, we just presented the definition of deterministic finite automata. And from now on, we'll just refer to them as DFA. So what is a DFA? It is a 5-tuple, right? A finite set of states Q, an alphabet sigma, a transition function delta, an initial state Q naught, and a set of final states F. So let me briefly write down the description of the various components. Please turn off your mic. And remember, an alphabet is always a finite set. Delta is the transition function. And you must remember that because it is a function for every state and every symbol in the alphabet, there is a next state. Okay. So the function must be defined for every pair of state and symbol. And F is a set of final or accepting states, right? Okay, and often it's instead of writing down this function, this transition function, or when writing down the description of a finite of a deterministic finite automaton, what we do is we use a graphical notation. Right? And we draw the states as circles. You can put the name of the state inside. The initial state is indicated by an incoming arrow. And the transitions are indicated by arrows, which are labeled by symbols in the alphabet. So suppose your alphabet is the binary alphabet 0, 1. Right? So this is the way we depict deterministic finite automata graphically, right? This is Q naught is the initial state. The set of final states is just the set containing Q1, and this is indicated by these double or concentric circles. And the arrows indicate the transition function. So for example, delta Q naught 0 is Q1, and delta Q naught 1 is Q0, right? And so on. You can fill out the details. I mean, there are only two states here, so.
Hello.
Yes.
Sir, can you explain how we got Q1 as the only final state?
This is how we define this automaton. This
Ah,
particular automaton has the set as the singleton set containing Q1 as the set of finals. Yeah. Okay. So I'm just illustrating the notation.
yeah.
If both Q0 and Q1 are final states, then we'll put a concentric circle around Q0 as well, right?
Yeah, okay.
Okay, right. But of course, this doesn't tell us how the how the DFA behaves. So for that, I already talked a little bit about how it reads inputs from left to right, makes state transitions starting from the initial state. And if at the end, when it has read the entire input, if it is in a final state, then the input string is accepted, otherwise it is rejected. But today we are going to formalize all that mathematically, right? This is a mathematical course. We are going to give a mathematical definition for every concept, right? So what I just said in words is formalized as follows. First, what we do is, I don't know why this is coming. Right. So the first thing to do is to extend this transition function from symbols to strings. Okay. What do we, sorry. So what do we mean by that? Well, here's the transition function. So this is extended to a new function which is Q cross sigma star arrow Q. What do we mean by an extension? Okay. Suppose f is a function from the set A to the set B, right? It is some function. What is an extension of f? Well, its domain is a bigger set than A, okay? Say A dash. And we say that the new function that we define, say f dash, that's an extension of f if it agrees with f on the elements of the domain A. So inside A, it is identical to f. And in addition, it uh, assigns values to the elements of A dash which are outside A. So that's what we mean by extending a function. Right? So it is really extending the domain of the function, right? As you can see, sigma star actually contains sigma. Why? Because sigma can be regarded as the set of strings of length 1. So sigma is sitting inside sigma star. So we are actually extending this function to a function on a bigger domain. And how do we do that? Well, by induction. It's an inductive definition, right? So we define delta hat so I say uh, define delta hat by induction as follows, right? So delta hat of any state Q and the empty string just gives you that state Q, right? And this is for all Q, all Q in a set of states Q. So that's the basis. And then delta hat of Q U followed by A, okay, where U is an arbitrary string and A is a symbol in the alphabet, okay? So this is a convention we follow, try to follow at least, throughout the course. If we use letters from the beginning of the alphabet, such as A, B, C, etc., of the English alphabet, then those are symbols in sigma. Whereas if we use letters like S, T, U, V, X, Y, Z, etc., those refer to strings. Okay, so this is a convention. But of course, if we write it out this way, then there's no scope for ambiguity. So how is this defined? So this is a string followed by a single symbol. So this is defined by induction. So first you apply delta hat to Q and U, and then apply delta to that. Okay. So is this definition clear? I'm just going to explain this through an example. As you can see, this is an inductive definition, right? The first clause defines the basis, and the second clause is the inductive case, right? So you define the value of delta hat for a given state and the string UA in terms of the value of delta hat on a smaller string, right? Which is delta hat QU. Okay, so is this definition clear? And of course, going to give you an example. Okay, so let's go back to the previous example here. So what is delta hat of Q naught 0, 0, 1? Okay, well, intuitively, this should be the state you land up in starting from the state Q0 as you process the string 0, 0, 1. So on a 0, you move from Q0 to Q1. And on the second 0, you move from Q1 to Q0. And on the 1, the third symbol, you remain in Q0 because of this loop, right? So this is, for this example, this is nothing but Q0. And of course, you should unwind the definition to see that this is indeed the case. And to do that, if you just go through the definition, then delta Q naught 0, 0, 1, if you unwind the definition, you get, sorry, what you get is delta hat Q naught 0, 0, right? So this is really the state you land up in when you process 0, 0, followed by the single transition, right? Yes, any doubts about this, what I have just written? I mean, this is just according to the definition I've just given, right? If you want to see it, here it is at the bottom. Delta hat QUA is delta applied to delta hat QU, comma A, right? So just use that definition. And this in turn is delta, another delta here, and delta hat Q0, 0, right, comma 0, and you have to close that, close the parenthesis here, and 1, right? And so on. You can go on unwinding until you get epsilon. And then, so the next step would be delta, delta, delta. So I've got 3 deltas, then delta hat, Q naught, epsilon. Running out of space here. Yeah. Followed by zero, comma 0. Did I get it right? Well, I have to close the parenthesis here. Delta hat. So this is delta. I don't know whether I've got all the parentheses correct. Well, you can match them. For some reason, it's not allowing me to draw a line here, but I don't know where this is coming from. But anyway, so and now you can see that delta hat Q naught epsilon is just uh, Q naught. That is the base case. Delta Q naught 0 will take you to Q1, and delta Q1 0 will take you to Q0, and delta Q0 1 will take you to Q0. Of course, this involves a number of steps of simplification. So any questions, any doubts about this? About this definition? It's a simple inductive definition. So um, it's just repeatedly applying the transition function, right? Yeah. Okay. So having defined that, uh, let us agree that from now on, we write delta instead of delta hat. Okay. So we use delta for both the transition function as well as its extension to strings. Okay. And there should not be any confusion because you always know from the context which function is meant. Okay. So this is like overloading in programming languages. So we overload this notation. Okay. Why? Because it's cumbersome to write this hat. Okay. Okay. So from now on, if you see delta, the first thing you should do is to figure out which delta is meant, whether it's the transition function or its extension, right? And we'll have to do it plenty of times, right? Starting now. So now we talk about the behavior of this finite of a finite state automaton in terms of this delta hat. That was the point in defining delta hat. Okay, we say that the DFA M, okay, so let me be more explicit. The DFA M, which is that horrendous 5-tuple Q sigma delta Q naught F. Sometimes it's difficult to remember the order, right? And different books have different orders. But as long as we know that Q refers to states and capital sigma refers to the alphabet, delta refers to the transition function, Q naught is the initial state, and capital F is the set of final or accepting states. This, I mean, you can write them in any order essentially, but Q usually comes in the beginning at the first position. Okay, so we say that the DFA accepts the string W belonging to sigma star, if delta Q0 W is an element of F. Okay. So which delta is meant here? Is it the transition function or its extension?
Extension.
Yes, it's the extension. So we could have written delta hat, but by the convention, we just write delta, right? So that's the first definition. This is the notion of acceptance. When do we say that a machine accepts a string, right? Essentially, it means that starting in the initial state, it'll land up in a final state after processing the entire string, right? That's what it means. That's when it is accepted. And otherwise, of course, it is rejected. So so this if is really if and only if, but usually in definitions, we don't bother to write if and only if. It is understood that in a definition, if means if and only if. I mean, you are defining a concept, right? Of course, in a theorem, when you use, there's a big difference between if and only if, right? And it has to be explicit, right? So that's definition one. Definition two, the language accepted by M, and this is denoted L of M, is the set of all words over sigma, or all strings over sigma, such that delta hat Q naught W belongs to it. So the language accepted by the machine or the DFA M is the set of all strings which are accepted by the DFA. Any doubts about the definition? To illustrate this, we can go back to our example, and I'll take lots of other examples, right? So what are some of the strings that are accepted by this DFA? Well, the string 0 is accepted because it takes the machine from Q0 to Q1, and Q1 is a final state. The string 01 is accepted, right? The string 01, 001 is accepted, and so on. Some of the strings which are not accepted are the empty string. Why is the empty string not accepted? Because delta hat Q naught, the empty string epsilon, is Q naught, and Q naught is not a final state, right? So for the empty string epsilon to be accepted by a DFA, the initial state also has to be a final state, right? Also, the string 1 is not accepted. The string 1 is not accepted, and so on, right? Okay, so what is the language accepted by this machine? Uh, I don't know whether there is a simple description of that language. Um, in English, uh, but you can think about that. Okay, let me give other examples which have uh, easier descriptions in English, right? But before we do that, strings having odd number of zeros. Oh yes, you are right. Yes. Uh, and why is that correct? Because any string with an even number of from starting from state q naught, right? If you read any string with with an even number of zeros, you uh, come back to q naught, and if you read any string with an odd number of zeros, you come to Q1. Okay. Okay. So on the left of this line, you have an odd number of. If you are in a state on the left of this line, and there is only one such state, you must have read an even number of zeros. And if you are to the right of this dotted line in any state, and there is a single state there, you are, sorry, you have read uh, an odd number of zeros. And you can prove this. I mean, this is intuitively clear, but you can also prove it by induction. Okay. Yeah. Um, thanks for correcting me. There is indeed a simple explanation, right? So let me take a few more. So that is the language accepted by this machine, right? Okay. Let me take a few more. Oh, there's one more important definition. A language, remember, a language is a subset of sigma star, right? So sigma is the alphabet. So a language is called regular if it is accepted by a by some DFA M, i.e. L is L of M for some DFA M. Okay. So these are the most important definitions in automata theory. What is the notion of acceptance? What is the notion of language acceptance? And what is a regular language? Okay. So now let us come to examples, and we have seen just one example. Okay. But of course, there are very simple examples. The empty set, right? The empty language. And let us fix the let us fix the alphabet to be the binary alphabet for these examples. Right? So the empty language is regular. Why is that? Because the single state DFA where for both, so this is a single initial state, and that is the only state. And the only transitions are, to that, back to that single state. So if this is the machine or the DFA M, so L of M is the empty set. Why? Because there is no final state, right? So there is no final state. So the language accepted, so the set of final states is the empty set, right? So the language accepted by this machine is empty, right? Similarly, sigma star, the set of all strings over this alphabet is regular. And you have to make only a small change make this state initial as well as final, okay? So in this case, LM is sigma star. Yeah? Any doubts? And by the way, the empty language is different from the singleton set containing epsilon. And this is also regular. And how is that? What is the machine that accepts this particular language? Well, as I said earlier, unless the initial state is also final, is also a final state, epsilon is not accepted. So this has to be the case. But then no other string is accepted. So you got to add another state which is non-final. And these are actually two. When I write a comma, it really means two transitions. So you transition on a 0 as well as on a 1. Okay, so this is used here as well. So that is the convention, right? And in this state, this is a trap state. So once you reach there, you are a dead state. So you just keep on looping there, right? Now, please understand that this part is needed. You cannot drop it. Why? You cannot drop that part. Why? Anyone?
So because then the language would change to sigma star. Because all strings can be accepted.
No.
Sir, for a DFA, the transition state must be there. So without that, there is no transition state. So it's not possible in that way.
So the answer is, yeah, just to rephrase your answer, delta is a function. It is not a partial function. It is a total function. Okay. In mathematics, when we say something is a function, it is a total function. It must be defined at for every element in the domain. Okay. So for every state, you must have a transition for every symbol. Okay. So that forces us to add this dead state. And also, it forces us to add the looping transitions for the dead state, right? So this is important. This is a function. Okay, some more examples. If anything is not clear so far, please let me know. This is really irritating. I mean, uh, third example again. Which third example? This one. Okay. This particular machine accepts the empty string because delta hat Q naught empty is Q naught, which belongs to F, right? And delta hat Q naught X is Q1, which is not in F for all X not equal to epsilon. Right? So if you take any string X other than epsilon, you can see that you'll end up in a non-accepting state. Only for epsilon do you remain in an accepting state, starting from the initial state. Does it answer your question?
So why should not we take second state in second example? Same state in second example for third example.
In the second example, let me just write it down here. Delta hat Q naught X is Q naught, which belongs to F, for all X in sigma star. This is for the second example. So for all strings, including epsilon, you land up in Q naught, and Q naught is the only state here. Right?
Yes.
The difference here is any string other than epsilon, you leave Q naught. And once you leave Q naught, you go to Q1 and you remain there. and this is non-final. So the only string accepted is epsilon. But here, uh, whatever string you take, you always land up in Q naught. Yeah?
Yes, sir.
Okay, more examples. We have already seen uh, odd number of, what did we see? Odd number of ones? Was that it? No, odd number of zeros, right? And again, let's take the binary alphabet. So we saw this earlier. So how do you reason about that? As I mentioned, when you are in state Q naught, you have seen an even number of zeros, okay? And when you are in state Q1, and the number of ones could be arbitrary, odd or even, doesn't matter. When you are in state Q1, you have seen an odd number of zeros, okay? And of course, you can prove it by induction on the length of the string, okay? Right? And I leave the proof to you. All these proofs that we are going to do will depend on induction. In fact, delta hat was defined by induction, and all proofs rely on the inductive definition of delta hat by using induction, okay? Usually induction on the length of the string. Yeah. Okay. Any questions about this example? Let's take some more. Suppose you want the language of all strings set of all strings with an odd number of ones. Sorry, with an odd number of zeros and even number of ones. Okay. So what we have to do here is make two copies of this machine. Think of this machine extended in 2 dimensions. Oops. So in the X dimension, we will keep track of the parity of zeros, whether it is odd or, so we'll keep track of parity of zeros, and in the y dimension, we'll keep track of the parity of ones, right? So this is what the machine will look like. So on zeros, the behavior will be the same as above. And same here. 0, 0. Okay, just as above. And then for ones, so for zeros, we move left and right. And for ones, we move up and down. So pretty cumbersome using this pencil. Right? So this is the idea. And this is the initial state. So let me label the states. This is Q0. This is Q1. I'm sorry, I've drawn the circles too small, but I'm too lazy to redraw the whole figure. So you have to strain your eyes a bit to read the, but it's not too bad. Right. Okay, now you tell me which are the final states. Q1 is the
Q.
answer. So the answer is there is only one final state, and that is Q1. Right? And intuitively, that is correct, because if you think of a dotted line this way, then above the line is even number of zeros. So let me just write even zeros. Sorry, ones. Even ones. And below the line is odd number of ones. And similarly, you can think of a vertical line, dotted line. So to the right of this is odd zeros. And to the left, you have even zeros, even number of zeros. And therefore, the only state which keeps, which sort of registers an odd number of zeros and an even number of ones lies to the right of the vertical line and top of the horizontal line. And therefore, there is only one such state, which is Q1. And again, you can prove, I mean, this is an intuitive reasoning, but you can actually prove this using induction, and we'll skip that proof. So any doubts about this example? I forgot a label here, did I? So these are ones. These are. Any doubts about this? Okay, let us proceed to more examples. L is the set of all strings how much time? Oh, it's time. Set of all strings that end with a 1. Okay, let me just describe the machine. This is on a 1, 1, 0. So think about this, and we'll stop here. If you have doubts, we'll take it up in the next class. Okay. That's the end of this class.